Morning, guys. So yesterday we introduced Newton's three laws, how it sort of summarizes some of the dynamics that we're going to be learning in this chapter. Newton's first law had said, unless you actually apply an external net force, unless there's an unbalanced force, objects continue doing what they're doing. So if the object is just sitting at rest, it just continues onwards at rest. If the object is already moving at constant velocity, unless you actually push on it, it's just going to continue sliding off doing what it's doing. If, in Newton's second law here, there is a net force that's actually being applied, we found that the net force was proportional to mass and acceleration. Larger masses are a little bit harder to accelerate. If you apply the same force, you can push lighter masses a little bit easier. We saw those relationships there. And then Newton's third law had said basically action-reaction. Pretty much every force that we have, every arrow that we draw on a free body diagram, they always come to us in equal and opposite pairs. Usually, we don't need to look at that level of detail, but that's always important for you to note. Usually in a typical free body diagram, we have many forces that we're addressing. Sure, each of the arrows themselves are in equal and opposite pairs, but usually we just look holistically and we say, what are the overall arrows pushing in every which way? We also talked about Hooke's law, which was basically the force along a spring. We had F is equal to kx. It's depending on the material of the spring and depending on the compression length. So I'm going to give you a quick practice question there. And then today's lesson will introduce friction as our force. So just as a quick warm-up here, let's start off with the spring. The thing to be careful of for a spring is the spring at first already has a natural length. So I'm going to say that the spring here currently is 100 centimeters. You can always convert this to meter later on. Right now, this is the relaxed length of the spring. So when I engineered it, it was about a meter long. What I'm going to do is I'm going to steadily put a 50 kilogram mass on top of it. Because there's now a weight on top of it, this spring here is being compressed tighter than it wants to be. And what's going to happen here is we put the 50 kilogram on top. And basically I just measure, well, what's the overall length of the spring left over? And this one here gives me here, let's say it's 60 centimeters. So imagine with no mass, right, the spring could be its entire length here. By putting the weight on top of it, it actually starts squishing down the spring here. Let's say I take a picture. At the instant it is at 60 centimeters from the ground, it happens to be still accelerating. So it still hasn't really supported the entire mass. But let's take a sort of analysis at this point here. Let's say the acceleration here is 1.0 meter per second squared. Now, normally you'd say to me, well, acceleration isn't supposed to be 9.8? It is 9.8 for gravity if this was in free fall, but you notice that here the spring is supporting it, even though we're sort of taking a quick picture of this one here. An instant later here, the spring would keep contracting a little bit more. It would keep sliding down a little bit, but you notice that the spring does support it enough that instead of falling directly 9.8, the acceleration is only 1.0. So let me just work through this problem here. We have an object is lowered using a spring with a constant k. So later on, one of our questions are going to ask you for k. The k unit will be newtons per meter, right? It talks about how much force is needed to stretch out that spring, squeeze it sort of 1 meter beyond what it wants to do. And again, in the picture it says with an acceleration of 1.0 meter per second squared. How come they don't say negative there? Because they already indicated for you here lowered, right? That means negative. They already pointed the arrow. That also means negative there. So in this question here, a couple ABCs. Part A, I want you to calculate the FG. Right? We always have a formula for that. And I want you to calculate the magnitude of the F net. I could have just said calculate FG and calculate F net. We'll talk about that in a second here. And then in part B here, I want you to find or determine the restoring force from the spring. Right? So again, if you can try it out for yourself, just pause the video. You can unpause it and you can give it a go afterwards. First thing I would do, they didn't ask me for a free body diagram, but that's always a good place to start. If I imagine this 50 kilogram block here is all squeezed into one center mass, I'm just going to draw a set of arrows talking about all the pushes and pulls on the center mass. So they helped me out here. They said, well, because we have mass, gravity's going to be pulling downwards here. There's an FG. For the spring itself, it used to be 100 centimeters. Now, because it's squeezed tighter than it wants to be, the force on the spring is what's supporting it. The spring actually now pushes upwards. So the spring is actually applying force. That's called the restoring force because it's constantly trying to get the 60 centimeter new displacement here. It's trying to get it back to the 100. It's applying a force going upwards. Those are actually the only two forces that act on my diagram. How come I don't list an arrow? Oh, F net, right? Remember, F net is just what's left over after you do the tug of war. So case in point here, because we know that this mass here is going to steadily get lower and lower, who's going to win in this tug of war, FG or FS? Who has to pull harder so that this object here can actually slide downwards? In this case, you should be able to say to me, well, if they were equal, the mass would just sit there. But because we have an acceleration going downwards, there's an overall unbalanced force that's downwards. The person that's tug-of-warring downwards is actually FG. I would actually argue FG is actually bigger than FS by the amount of net force. So let's calculate FG here. We always have a formula for this here. FG is just M times G. So we're going to go, we are a 50 kilogram mass. The G is going to be 9.8. This one here gives you 490. Pretty much every mass, you're going to assume that we're on the Earth's surface, so 9.8, it's going to be 490. If the Fs was equal 490, this object here would be at, there would be no net forces acting on it, it would move at constant velocity. But because, like we said, wait, there has to be a wind of 1 meter per second squared, if you just use Newton's second law, F net is equal to ma, keep in mind, again, I tried to emphasize, F net is not a force. F net is not something that actually pulls in the tug of war. F net is just what's left over after you deal with the tug of war. And in this case here, we're sort of working backwards. We're sort of saying, well, I know that this 50 kilogram object, I know it actually has an acceleration of 1 going downwards. We have to have a net wind of 50 newtons downwards. So when you look at the tug of war between FG and FS, FG has to pull harder by 50. In that case there, we can then find what the FS is. So how this is going to look here, again, you're not going to get this on any formula sheet. You have to look at the scenario here. F net is what's left over from the tug of war. Because I know the FG wins, I know this thing here actually accelerates downwards, I usually go bigger minus smaller. So I'm going to go FG minus FS has to give you that 50 newtons. Right? Again, that's just purely for this situation. If we had just calculated, well, FG was 490, right, M times G, what does the force on the spring have to be so that there's a net win of 50? The FS would have to be 440, right? And you can always just double check whether I did those numbers right here. Let's imagine you're standing in the middle, and let's imagine you're being pulled downwards 490, and you're being pulled upwards 440. Right? In that case there, you'll eventually go downwards. The net force, the net unbalanced amount is going to be 50, and that 50 is exactly the magnitude, is exactly the size I need for a mass of 50 kilograms to actually accelerate 1. So again, we use this idea bigger minus smaller. Now we've actually found the restoring force. This is the Fs. We're going to actually find the spring constant. So find the restoring force from the spring. I got it. And then we just use Hooke's law here. Fs is supposed to equal to Kx. Yesterday, in some cases, I put negative Kx. You just need to be careful. Negative is just opposite. So if Fg is squeezing the spring tighter than it wants to be, Fs is pointing upwards. It's trying to restore it back to that 100 centimeters. If my force along the spring here has to be 440, we're going to totally avoid problems of positives and negatives just by labeling a free body diagram. When I say Fs, well, I know Fs is in a totally different direction than Fg. Instead of putting one of these negative, I can see from the arrow Fs is pointing upwards. It has a size, a magnitude of 440. I don't know the K constant. The X, remember, is the amount that's stretched beyond what it wants to be. The natural length used to be 100. It's now 40 centimeters tighter than it wants to be. It's just that I want it in meters later on, so I'm going to put 40 centimeters in meters. So I'm going to divide over the 0.4, and we'll see what we get here. 440 divided by 0.4 gives me here 1100 newtons per meter. So that is a spring constant. That depends on the material itself. That says right now the spring is only supplying 440. That's why the spring is not even compressed by a meter. If you want to compress it for every meter that you want to stretch it in, you actually need to apply 1100 newtons of force for this to completely squish downwards here. Again, what we did in this problem here is we just took a quick snapshot because I know, well, eventually the spring is going to keep contracting. Eventually here, because the displacement is going to be a little bit higher, the amount of force on the spring is going to be steadily higher. Hopefully the spring will later on get to some new length that it can actually completely support the force, so it completely have no net force. But it's just a little bit more interesting sort of midway here. It is still in motion, it's still happening to accelerate, and at this instant of time, we've done our calculation. So we're going to practice more of these here. Today we're going to look at the idea of friction as a force. We had mentioned before, friction is a contact force, so it requires surfaces to be touching. And one key word that we're going to see in this lesson here is for a contact force, this contact force that opposes motion. Friction is just trying to slow down everything, it's trying to bring everything to a rest. If you pull the object to the right, it pulls to the left. Does it really like left? No, not at all. It just doesn't like the fact that you're pulling it to the right. If you pull it to the left, it's going to pull to the right. So it's going to always oppose motion. We're going to see once motion has been stopped, friction sort of has its way. So let's just start off here with like a box just sitting on a surface. Again, what we do is we always just do a free body diagram, even if they ask it for you or not. Basically, we're going to imagine, instead of this box here actually having a size and a shape to it, we imagine taking all that mass and squeezing it into a center point, center of mass. We're going to do arrows. Try to do the size of the arrows representing which arrow is larger. So in this case here, I always do it in order. We always have an FG. That's going to be m times g. In this case here, as you imagine, if I'm looking at this box here doesn't suddenly fall through the ground. So that means the ground itself has to be supporting it. 2 days ago, we talked about what's called a normal force, a force that's perpendicular to the surface. Basically, the electrostatic forces along the different atoms and all that, they end up supplying a force here that has to go upwards. Remember that whole notion of equiopposite? It does not mean Fg is equal to Fn. That's not the equiopposite. When I say equiopposite, I mean more so something like, well, as the Earth pulls on the box, so the box pulls on the Earth. That's an equiopposite pair. As the ground pushes up on the box, that's one. The box also pushes down on the Earth. That's another equiopposite pair. So that's why we don't really worry about Newton's third law. That's because it's a little bit too technical. What we do is we just look big scale. We say, well, there is one force having its equiopposite pair. One force pulls it downwards. We actually see that in this case here, oh, actually the Fn does actually have to cancel out. Not because of the equiopposite, but because I can see the answer. In this case here, the box here doesn't pop off the ground because of the ground. It doesn't fall through the ground because of gravity. So right now I'm saying Fg does have to equal to Fn, but that's something unrelated to Newton's third law. What I'm going to do this time is I'm going to apply a force. So I'm going to say Fa. Sometimes you hook on a string and you can label it T. It really doesn't matter what you label it there, but just note that this one here is an applied force. This is what you decide to do. I can pull it with 10 newtons, 100 newtons. This one is completely up to me. No matter how smooth the box feels to us macroscopically, or the ground or the floor feels to us macroscopically, if you zoom in to the surfaces, the box, at the bottom of the box here, there's all these little microscopic grooves. So that's sort of the box on top. There's also some microscopic grooves here on the bottom. And again, right now they're currently at rest. Right now the box is just sitting there. It doesn't mean that the grooves are perfectly interlocked. But what I want to show you here is, because there is a certain roughness, what we're going to define is something called a coefficient of friction. There is going to be a friction coefficient. We're going to label it with mu. Right, the friction coefficient mu, and I'm going to give it, in this case here, let's say a mu of 0.50. Basically, this friction coefficient describes how many grooves do each of the surfaces have, and basically how interlocked the grooves are. How much do these surfaces want to just sort of sit there and not really want to move? So that's the friction coefficient. This number never gets to be really big, so maybe it gets upwards of maybe friction coefficient of 1 or 2. But if you're calculating something like friction coefficient 30 or 400, probably something is off, right? So in this case here, I just arbitrarily decided to pull things to the right. That means friction is going to go against me, and friction is going to go to the left, right? So the way we sort of study these forces here, I would always try to do it in this order. It gives you a nice sort of routine way of doing it. Start off with Fg, because Fg you always have formula for m times g. In this case here, well, I haven't given you a mass yet, so let's take a look. Let's say this mass here is 30 kilograms, right? Well, let's just multiply the 30 by the 9.8 for being on the Earth's surface here. How hard is gravity pulling on you? 30 times 9.8. This gives you here 294. Notice again, I didn't have to say a negative 9.8 and a negative 294. Because I have the free body diagram, I can see that the Fg is actually pointing downwards. The Fn is the next force. The Fn was a little bit annoying. You don't have the formula for it, but this one, the ground just supports what it needs to. So in this situation here, because gravity is pulling at 294, I sort of know the answer in the vertical. It neither pops off the ground or falls through the ground. That means the Fn has to equal gravity, so Fn also has to be 294. Normally I put one of these positive, one of these negative, but again, because I have the diagram, I see that these are opposites to each other. At this point here, I'm going to introduce to you the friction formula. So for friction, the FF, this is going to be our third force. The reason why we do it in that order is the friction force definitely depends on this friction coefficient, this mu constant, basically how rough these grooves are interlocked, but it actually deals with the Fn. So only after you calculate Fn can we then do this friction formula. So this is another formula here on your formula sheet here. I'm going to mention here this FF is the maximum friction. Right, that's going to be in newtons because it's a force. Mu, again, is this friction coefficient, describes the roughness, and then this Fn is like we knew, it's the normal force. The normal force here is sort of the apparent weight, and there we go. All right, so let's just punch our way through the numbers. So if FF is equal to mu times Fn, mu is 0.50, that's the roughness of the surfaces. The apparent weight that we have is 294. Remember, we had said this 294 essentially is the positive of gravity. Gravity was 294 as well. So we have 294 here. So therefore, the max amount of friction against me is 294 times 0.5. It's equal to 147. Essentially, there is enough roughness between these surfaces to hold you back by 147. All right? So I want you to just sort of consider a couple situations here. If the FA is, let's make it 100 newtons. All right? So the box is just minding its own business, just sitting there. If you happen to start pulling at 100 newtons, what happens to this box? So far I've said, based on this box here, we had gravity pulling 294. We had a normal force going 294. In the vertical direction, these ones here cancel. So there's no unbalanced force here. That's why this object neither goes upwards or downwards. What about in the horizontal direction? For the horizontal direction, we have a friction force, conveniently going to the left, and we have an F applied force that's going to the right. Looking at the numbers, going to the right here is actually 100 newtons, because I just listed that for you there. And the FF we calculated as maximum is actually 147. If this were truly the picture, what's the net force? Well, again, we go bigger minus smaller. The up and down forces are canceled out. Looking at the left and right, well, friction is pulling 147, and I'm only pulling 100. Well, that means there's a net force going in the leftward direction. And if there is a net force, there has to be an acceleration also in that direction there. Does that make sense? Well, this object here was at first sitting there, right? I didn't apply a force yet. I start pulling on it. No doubt, I'm not pulling hard enough to overcome friction. And yet, as I pull to the right, suddenly friction pulls it to the left. Well, no, that doesn't make any sense. Here's what I want to emphasize here. This formula here gives you the maximum amount of roughness. Friction is also lazy like normal force. So basically, if friction realizes, oh, you're just pulling 100, I don't need to even go all out against you. I don't need to go 147. All I'm going to do is I'm going to say, because I oppose motion, as long as friction, let's drop my friction down to 100 newtons. If I can supply 100 newtons against you, I've already canceled your force. There would be no motion, and therefore, I've done my job. So this formula here, FF equals mu Fn, it's nice in giving you the maximum amount of friction, but especially in this case here, let's just write down in words. Since Fa is smaller than friction, friction only uses 100 newtons and has stop motion. That's all it needed to push to get rid of your 100 newtons. And when it's stop motion here, this object just continues at rest because there is no imbalance force. Newton's first law says if we were at rest, we just stick at rest. So what gives then? How do we actually get this object going? Well, we had calculated with the formula the maximum friction is 147. You actually need to pull harder than 147. Again, I want to emphasize here, this is not an equal and opposite kind of thing. The equal and opposite is applying the friction force as itself, the applied force as itself. You can pull any hardness regardless of what the friction ends up being. And in fact, if friction maxes out at 147, if I pull any more than 147, 148, 200, if I pull that, I'm going to pull so hard, friction is going to try to stop me. But friction, because there's only so much grooves along the surface, that it can max out 147. Overall, I could have a net force going forwards, and that essentially is going to cause my acceleration. All right? So in this case here, because friction doesn't need to go all out against you, it's just 100 newtons, it just cancels the net force. It makes the net force 0. When we have a net force of 0, it means there's no net acceleration. The object just continues doing what it's doing. Just a little bit of detail here. Right now here, the box is at rest. So imagine this is sort of the bottom of the box's surface. The grooves along the bottom, again, they're sort of interlinked here. It really depends on how smooth the objects feel. But again, macroscopically, we can't feel these little tiny ridges here. At this moment, let's imagine this box here is currently at rest. It's just sitting there. Right now, I would say the grooves are sort of maximally interlocked. They may not be exactly filling up all the pores and all the holes, but all I'm saying here is the grooves themselves are really like sitting into each other, really digging into each other. In this case here, when we actually define a mu, we can actually call this mu, mu s, and this is actually the static friction coefficient. This is just a little bit of detail for you. For problems, I typically don't do this level of detail, but in this case here, a static friction coefficient, we've seen the word static before. Static means if the object starts out at rest, it's not moving. You need to actually start pulling hard enough so that these grooves here can actually come out of each other, so that you can actually drag this box here. Let's get it out of these grooves here and actually get it sliding along. So in this case here, we need to overcome. Fa overcomes the static friction to get moving, right? So right now here, it was already currently at rest here. That could be this, the maximum friction is 147. You have to apply at least 147 to get it going. What I want to introduce to you here is, let's say I do that. I start pulling 148, 149. I start sort of overcoming. I get the groove sort of out from one of the other. Now the object, the box here, is just actually sliding along, sort of same number of grooves there. This time, because the object is actually in motion, I'm actually not giving it a chance for the grooves to actually interlock. Sure, the little peaks there will still jostle and still sort of knock against one another here. But in this case here, because the object is currently moving, I don't care if it's constant velocity or accelerating, because the grooves themselves are not fully interlocked together, the mu coefficient is actually a little bit less. In this case here, mu again describes, well, how rough are the surfaces. Usually we call this mu k, and mu k is basically called the kinetic friction coefficient. And let me just write down the words here. As the object is moving, the grooves I'm talking about sort of the bumpiness on the bottom of the box or the top of the surface here, the grooves don't interlock as much. So therefore, as a general rule, the mu k is usually a little bit less. It's still a friction, right? It's still trying to slow you down. It's still trying to keep you from completely just running off there. But the mu k is usually a little bit less than the mu s. Now, when I mentioned here, well, for typical problems, we don't usually do this level of detail. Usually, they just give you one mu coefficient. They just call it mu, and this mu here sort of covers. Well, which part was it just to keep it from moving? Which part of it was even after moving here, even though the grooves aren't as interlocked as before, even though the mu k should be a little bit less, they usually just call it one and the same, just mu coefficient. So just watch out for that. Again, the emphasis here is there's only enough grooves on the surface to interlock to a certain degree. In this case here, it maxed out at 147. Sure, if you pull anything less than 147, the friction will match it so that the object will have no acceleration. If you pull anything harder than 147, we'll do that in the next question here, we'll actually get it to actually move. One other note here before we do that situation, this is actually a little bit strange of a formula. FF, looking at the directions, FF is actually a horizontal force, whereas FN is actually a perpendicular force. I thought we went through the whole kinematics chapter saying because the x and y are independent of each other, x can't affect y. That essentially is true, but using this sort of notion of grooves here, let's start off here with the box just sitting there like we have in the problem here. Right now the box, again, has some grooves on the bottom of the box here. It's interlocking with the grooves with the ground. What if I now sat on this box here? As I sit on this box here, I add an extra amount of mass, right? So gravity pulls down on my body as well as the box itself. What's going to happen is because the FG is now larger, if you sort of zoom in macroscopically here, at first the grooves were already kind of interlocked, like the boxes, and then we had the grooves on the bottom of the surface here. When you now sit down on it, because you've now increased the FG, what you've actually done is you've actually squeezed. The box's grooves here are a little bit more interlocked than before. You're right, vertical doesn't affect horizontal, but in this case, the vertical, as denoted by the FN here, the FN actually sort of talks about here, how much are you sitting down on it, how much harder are the grooves actually interlocked, and therefore, because the grooves are trying to keep this from any sliding left and right motion, you will now need to pull even harder to actually get the box's grooves out from one another. So that still is true, X doesn't affect Y, but in this case, it's actually the grooves that are interlocking. When they interlock more deeply, it's a little harder to get the grooves out from each other. So let's just finish off this problem here. Let me just take a note of some of my numbers. We're going to go with our box. We had already said here, gravity was 294. The normal force went against it. That had canceled out, right? I sort of know the answer here. In the vertical direction, it doesn't pop off. The maximum friction we had said was 147. Let's say this time I actually start applying a force, right? It's up to me what I pull. And I'm going to apply 200 newtons. This could be me in the front pulling the box. It can be me behind the box pushing the box. But nonetheless, here there's a force that's going 200. At this point here, if FA is 200 newtons, we look at our picture. Well, we say in the vertical direction, the FG and the FN they've canceled out each other, right? The verticals are completely gone. But in terms of the horizontal, the tug of war is I'm going 200 to the right. There's only a maximum of 147 against me. If friction could, it wants to actually go 200 to stop you. But again, we had calculated there's only so much roughness on the surface to actually go 147. That means you have a net force. You have an overall wind of bigger number minus smaller number. You have 53 Newton wind going to the right. And once you have that net force, we can use Newton's second law. Only after you calculated that, then you use this formula here. If I have a wind of 53, here comes my mass again. Mass is 30 kilograms. What's my acceleration? So as I drag this object to the right here, I overcome friction, and now this block here accelerates at 1.8 meter per second squared. Just a note on a later lesson here, once you get the acceleration, you're more than welcome to do your kinematics again. This object here started from rest. If I give it 5 seconds of time, you can find final velocity, you can find displacement. This acceleration actually gives us a connection back to our kinematics. So practice your way through some of those worksheet questions, and we'll pick it up from there tomorrow. Thanks, guys.